Umnik. I will be solving second division the first round 1005, and I will try to explain what I'm doing. Given a binary string, the initially empty binary string t, can make moves any number of times. Remove some suffix from s and place it at the end of t, or remove some suffix from t and place it at the end of s. Okay. To win the contest, you must make the minimum number of moves required to make s contain only the character 0 and t contain only the character 1. Sounds like the answer would depend only on number of groups of zeros and ones in the original string, and like we should suppose that before the string there is a number 0, and it looks like the answer is just the number of groups minus 1. Like here we have one group, but not actually, because there is a 0 in the beginning. I think it shouldn't be hard to prove that. Something like we need to look at the places where the number changes in each operation. We can only reduce it by 1. In the end, there shouldn't be any, so that's the lower bound on answer, and shouldn't be hard to construct the example, like how to do it with exactly that number of moves. It's kind of sad to me that like I didn't do the screencast with commentary for half a year, and the first problem is like guess the answer from the sample, which I'm usually against doing, but I think it's actually the best way to solve this problem. So problem B. The score of array is defined to be the length minus the number of distinct elements. Okay. Have an array A, you need to remove some non-empty contiguous subarray at most once. So you can remove like empty ones, whatever. output an operation such that the score is maximum. Wouldn't that like be doing nothing? So the score is like the number of elements that are not the first occurrence. So if you go left to right and you mark first occurrence of every element, then every element that is not marked gives +1 to score. So like not removing anything is the best you can do. If there are multiple answers, output one that minimizes the final length of A. Okay, so we would like to not remove anything, but we can try to remove something but still achieve the same score. To do that, we would have to only remove elements that are unique, because if you remove an element that is not unique, you obviously decrease the score. So we just look at which elements are unique, and then we want to find the largest subsegment of the marked elements. Okay. If you wish to not make a move output 0, otherwise output to integers. Okay. So I read the array and count the number of occurrences of every element. And then for every element, if it is unique, then it is good, otherwise it is bad. So let's say that good elements are ones and the bad elements are zeros. And now we want to find the largest segment of consecutive good elements. If we haven't found anything, just print 0, otherwise print the segment that we found, and it should be like this. Problem C. Have array of consisting of non-zero integers. So they can be negative but not zero. Okay. Initially you have 0 coins and you will do the following until A is empty. So supposedly we will remove some elements. Select an integer I, gain absolute value of AI coins, and then if it was negative, we only leave the prefix before that element, and if it was positive, then we only leave the suffix. Find the maximum number of coins. interesting. Alright, should be one. So in problem C, it looks like we need to consider what will be the last element we want to remove. So like each time we choose an element, we will remove the prefix or the suffix. So yeah, let's find the last element that we are going to remove. So this one is the last one. Then we don't want to delete it with all the previous operations, which means that on the left we only want to remove the prefix, and removing the prefix means we can only take positive elements, and on the right we only want to remove the suffix, so we only want to take negative elements. And since taking any element gives us coins and we want to maximize the number of coins, if we fix this one, we just want to take all the positive elements on the left and all the negative elements on the right. And we can take all of them, because like for positive we just go left to right and remove bigger and bigger prefixes every time, and for negative we will go right to left. So basically we just we can also say that like so this will be also like the negative element, so we just choosing the split point, and to the left of that split point we're choosing positive elements, to the right negative. So for every prefix find the sum of all positive elements on it, for every suffix the sum of all negative elements, and then just iterate over the split point and choose the best option. Problem D, 5-second time limit. There are n slimes, has weight vi. Slime I is able to eat another slime j if vi is at least vj. Afterwards, slime j disappears and the weight of slime I becomes XOR. Interesting. Usually it's sum. Okay, XOR. And I and j don't have to be neighbors. We can just take two slimes and one eats the other. The king of slimes wants to run an experiment with parameter x as follows. Add a new slime with weight x to the right end of the line. This new slime eats the slime to its left if it is able to, and then takes its place. It will continue to do this until there is either no slime to its left, or the weight of the slime to its left is greater than its own weight. The score is the total number of slimes eaten. Apply queries, blah blah blah. Note that the king does not want you to actually perform each experiment. His slimes would die, which is not ideal. He's only asking what the hypothetical score is. In other words, queries are not persistent. Okay, so the order actually matters, and we only consider like going from right to left. That seems like mostly an implementation problem, because of the operation is XOR, and we apply it only if the weight we eaten is not greater than ours. Like, in a sense, our weight will decrease during the operations, or rather what will happen is following. Let's look at the highest bit of our weight. So our current weight is something like this. This is our highest one bit. We know that we will eat the next slime only if its weight is at most ours, so it cannot have higher bits. Its higher bit cannot be bigger than ours, so it's surely like 0, 0 here. Then we can have two cases. Either it has the same highest bit, or it is strictly lower than ours. If it is strictly lower, like this, or maybe like this here, when we do the XOR, only the bits starting from that highest will change, so our highest bit will stay the same. And it doesn't really matter like whether our number increases or decreases. We know that the highest bit stays the same, and also if we know that the highest bit of that other number is strictly lower, then our number is surely strictly bigger, so we will do this operation. So what will happen if the highest bit is the same? Well, then after the XOR, this will be 0, and then something will happen, but the result of all that is that the position of the highest bit will be moved to the right, and so our highest bit decreased, and it can only decrease further later on. So how can we can try to solve the problem we are given is that we want to so the problem we are given is like there is an array, and we have queries of adding a new number and then trying to go from right to left, eating smaller numbers and XORing with them. So what this thing said to us is that we cannot eat numbers with highest bit higher than ours. We will surely eat all the numbers with highest bit lower than ours if we encounter them. but when the highest bit is the same, maybe we eat it, maybe we stop, but if we do eat it, our highest bit will decrease. So our strategy would be to find the first situation when the highest bit is the same. So we eat everyone here. We can just pre-calculate prefix source so that we will be able to apply all that batch of operations quickly. Then we look like what is our current number, compare it with this one. If we stop, we stop. Otherwise, we apply this operation. Our highest bit strictly decreases, and we can try to continue. Since the highest bit is it has just 30 possible values, right? Our numbers are up to strictly smaller than 2 to the 30, so the highest bit is at most 29. So we will have just logarithm number of those jumps, and like the simplest way to do that would be just to store for every highest bit like the position of the number with that highest bit, and then do a lower bound in that list to find it. But actually we can we can pre-calculate for every position. So let's say we stay in here and our current highest bit is k. We can pre-calculate what is the next number with highest bit this or higher, because we also stop in that case. So we will pre-calculate like a matrix of n by 30. Like what is the next position where we need to consider. And then we can do each jump in constant time. We just know where to jump, do the jump. So actually the solution would work in like n plus q log c. But yeah, I guess the time limit is higher to allow that additional logarithm if you want to do another lower bound. But probably like log and lower bound is not good enough. Although I don't know. Okay, so first thing we do is, well, obviously read the numbers, and we will also calculate the prefix source. Now for every position, I want to find like the previous place where a number had highest bit at least this value. So you can also do it like here. I want to understand what to do with zeros, like how to implement it the best way. Okay, so the weights in the array cannot be zeros, so all of them have the highest bit. So if our number becomes 0 at any point, we just stop right there. Okay. Okay, so while we have some elements on the left, we want to look what is the closest element with highest bit not lower than ours. Ours highest bit can be found as well, you can do it in just search operations, it will be still fine, but there is like a built-in function clz, count leading zeros. So if we stay in position P, then our number is this, because we have already eaten the suffix. Or like you can just store this number in X, that's just a matter of preference. So this function counts the number of zeros, of leading zeros in that number. So the actual value, like the position of the position of the highest bit will be 31 minus. Okay, so that means that the next number we need to consider is here. If it is -1, so we just don't find another stop until the beginning of the array, or that number is strictly greater than our number like before eating that one, so it will be this. Then we stop before eating that number, so we do p++ and then break. Otherwise, we arrive at that number, it is still not greater than us, and we eat it, and that should like decrease our highest bit position, and we continue. And the answer here is just n minus p, right? The number of elements we have eaten. still wrong. This is very weird. This is right, but then this is not. Oh, right, because here I need to do it the other way around. The highest bit of that number is k, so for all the lower bits it is important. Okay, that does look better. I mean, that's not a lot of printfs. Should be fine. Problem E. Steve has a permutation P and an array C, both of length n. Steve wishes to sort the permutation P. There's an infinite supply of colored sand blocks. Using them, he discovered a physics-based way to sort an array of numbers called gravity sort. For all I such that from 1 to n, place sand block of color Ci in position ij. Apply downwards gravity. Oh, the colors for different positions can be the same. So here for positions 2 and 4, both use color number 1. Okay. Alex looks at Steve's sand blocks after performing gravity sort and wonders how many pairs of arrays would have resulted in the same layout of sand. Modulo something. Okay. So the first column will just stay the same, right? So the first column gives us the order of colors. So it's like 2, 1, 4, 1, 5 in this case. So the array C is actually fixed by this picture. What is going on with other columns? So when we look at the second column, it's just the relative order of colors if we ignore the value 1. Here was the value 1, so it doesn't produce any blocks to the right of it, and so in every column they will just fall down, like preserving the relative order, but we ignore 1. So basically this picture tells us like the elements that we deleted. So basically when we go from the first column to the second column, we know that we removed the element that was equal to 1, in the permutation P. And we also should be able to figure out more or less the position of that element. So like, from this column to this column, we have erased one of the blocks. And here we can determine uniquely that this was this green block. We will always be able to determine the color of the block. But maybe, like if orange was also green, right? We would have like blue, then 3 greens, then red. And in the second column, it will be blue, 2 greens, and then red. And we would be able to say, okay, so we removed one of those greens, but we don't know which one. And the one we removed was like the position of number 1 in the permutation. And I want to say that we can choose any one of them, just put one there, and then restore the like remaining permutation from 2 to n, and then like, insert one on the position that we have chosen. So now the answer to the problem would be just like consider those like segments of blocks that colored the same, where we remove one of the blocks, and somewhere in that segment we should have put like number 1, then number 2, then number 3, and so on. So the lowest number that is left, because we will remove it when we go to the next column. And so the length of that segment is the number of options, and we just multiply those lengths. Okay, so what's left is to we cannot actually build all that picture because it has like size n square. So we are given like the initial permutation and list of colors, and we need to like smartly understand what is happening with those colors in that form. So like on the first iteration we will look at the position of 1, and we want to find out the segment of like the same color that contains this position, and then remove it. I think we should be able to do that with like some sets and DSU and stuff like that. So we will store all the positions that are still alive in a set, and we will also store disjoint set union on those positions, and they're in the same connected component if they're currently in like in the same segment of some fixed color. So when we want to solve for element, we look up its component, multiply the answer by the size of that component, and then we need to cut that element out. So we remove it from the set. It has left and right neighbor in the set. So those two might have become like their segments might have collided if they were the same color. So if those two neighbors are the same color, we can join them in DSU. And also, like, when we remove the element, we also like subtract one from the size of the component. So I guess like it won't be the size, it will be just like the characteristic, the number of alive elements in that component, because the size is needed for DSU to work. I think it would be okay to just like change it. Probably that like the complexity of DSU would still be okay, but I'm not willing to risk that. Okay. I understand that probably the explanation was not great, but I think with code it will be reasonable to understand it. So I have rewritten DSU, have added another parameter like size of the number of alive elements, so that I don't mess with size. When I do unite, I need to add the numbers of alive elements. I also need to calculate the answer modulus, so I'm using pre-written mint for that. Okay, so we are given a permutation and the colors, but that permutation I actually want to go through elements in order of their value. So when I read the permutation, I will actually just write down that value P1 is on position 1, value P2 is on position 2, and so on. So it will look like this. I'm reading X, doing X minus minus, so that everything is 0 indexed. And so like this element was on position I in the permutation, so I'm saying like the position of the number X in the permutation is I. I will also need a set of alive numbers. And I need to do the merges in DSU that like, the elements that are in the same segments from the start, I need to find those. So if the colors of two consecutive elements are the same, then merge them in DSU. So now I'm going through the elements in order of value. The position of the element is I. Now I will take the component where that element lies, multiply the answer by the number of alive element in that component, and then decrease it by 1. Okay. And find where my element is in the set. Find its left and right neighbors. If both of them exist and they are of the same color, then unite them in Div2. That's it. I need to remove my element from the set, and that's it for real. Okay, so let's go through it once again. When we draw the permutation like that, the number x, so number 2 for example here, means that in the first 2 columns there will be a block for this row, and after that there won't be. So number 1 stops after 1 column, number 2 stops after 2 columns, number 3 stops after 3 columns, and so on. So each time we move to the next column, there will be 1 less block, and it corresponds to the, if we go from column number I to column number I plus 1, it corresponds to the number I in the permutation. So the each time we go from column to column, when we move all of that down, we just remove one of the blocks that correspond to the currently smallest number. So we just go through numbers from 1 to n and remove the corresponding block. But now we don't know which number corresponds to which block. But we do know more or less how they are deleted from the colors, and we can always find one block that might have been deleted, but actually the whole segment of blocks containing this one that is of the same color, any one of those can be the one we seek. So we just can choose any one of them, then remove it. The next column will be the same. We didn't assign any numbers to non-deleted blocks, so it's fine. So to solve the problem, we need to emulate that process, and on each iteration find the size of that segment from which we want to remove a block. To do that, we are maintaining those segments in disjoint set union kind of structure, and also having a set of alive elements so they are sorted by the position. And when we know which element to remove, we find it in the disjoint set union, find the current length of corresponding segment, multiply the answer by it, remove it by 1, then take out that element, and maybe 2 segments nearby have collapsed into 1. And the last problem, problem F. Given an array of lengths n and integer k, an empty array b of length epic if there exists integer I and minimum up to that element plus maximum when the suffix starts on the next element is equal to k. Count the number of epic subarrays of A. Subarrays means consecutive. Okay. And the elements of the array up to n that might be imported. I like this new, well, relatively new trend of not making the like coordinate compression necessary. Like if the values of numbers are not important, only like the relative order important, or like whether they're equal or not. Nowadays problem setters just make them from 1 to n, so that you don't have to do coordinate compression to not mess with complexity. But here it is not a situation like that, because like we take a sum of two numbers, compare it with k. Like if the numbers were bigger, it would be a different problem. So maybe it is important that the numbers are up to n. Minimum on prefix and maximum on suffix. The interesting thing here to notice and not forget about it is that we're counting the number of arrays such that it is possible to split them into prefix and suffix with this property. It is not the same as counting the number of possible splits, because one array can have several ways to split it, and we should be careful to count the arrays, not the splits. Although like it is probably easier to look at the splits, and so I guess we should start with that. So, okay, so there is big array. We then choosing subsegment of that array. And then in that subsegment we are choosing how to split it into two non-empty halves. Then we calculate minimum here, maximum here, and their sum is supposed to be k. K is given. Okay, so minimum is somewhere in the left part, maximum is somewhere in the right part. We can try to fix those two values. Then, so if this is x and this is y, then we know that x plus y should be equal to k. Also, all the elements here are at least x. All the elements here are at most y. If we fixed the position of those two elements, then we need to check if it is possible to split to find the split between them, so that in the left part everything is at least x, and the right part everything is at most y. but then also choose left and right border. Choosing left and right border is independent, but but like for those two pairs, I mean, there can be several ways of choosing positions of minimum and maximum for the same array. That is not great, but I think we can work around it if we still like fix x, y, check that there is a way to split in the middle, then we will find like possible left borders. Basically, we should choose left border such that all those elements are at most x. So basically for this element we just need to look at where was the closest strictly smaller element, and we should put left border somewhere here. So like possible left border somewhere here, possible right border somewhere here. Then we can draw on a plane. Basically, the segment is a point on a plane where x coordinate is left border of the segment, the y coordinate is right border of the segment. Since our like choosing of left and right border is independent, it means that for left borders we have some good segment, for right borders we have a good segment, and so like this pair of points would give us like this rectangle, like every point in this rectangle is good. And then if we find all those rectangles for all possible pairs of like ways to choose position of minimum and maximum, then we need to find the area of union of those rectangles, and this is a standard problem that can be solved with scanline with Fenwick. So the issue right now is that well, first of all, I need to understand how to do that, but that's like secondary. There is a very big issue that number of ways to choose this pair of points is quadratic. We can try to overcome this using the fact that there's the sum of values is fixed, but the values themselves, like they can repeat, right? So it can still be quadratic number, but we can try to like fix a pair of values that sum up to k, and then consider them like together somehow. So let's say that we have fixed x and fixed y. And so let's look at all the occurrences of x in our array, all the occurrences of y. It kind of seems that like it's dumb to choose x and y very far away from each other. So let's say that we have chosen this x and this y. There is some split between them. Okay. Surely, if the split is fixed, then surely we want to choose the closest x to the split and the closest y to the split. That must be true. Well, yeah, that is true. If we're choosing x and y, then we need to find whether there exists a good split. If that good split exists, for that split and for like pair of L and R chosen, we could choose like just the rightmost minimum on the prefix and the leftmost maximum on the prefix. Okay, so then it should work okay, right? Like, I can try all the splits. For the split, choose the closest x on the left and closest y on the right. Technically, it's a lot, but I don't have to choose like all the splits. I need to try all the splits like between 2 points. I just need to look at all the possible options for what is the closest x to the left and closest y to the right. So obviously, while I'm moving between 2 points of interest, that doesn't change. And like it can be kind of like somewhat counterintuitive. So like this blue point and this red point are a good pair, even though they are not consecutive in any way imaginable. Like there are closer red points to this blue, there are closer blue points to the left of this red, but there is a split such that this blue is closest on the left and this red is closest on the right. So I need to consider all the splits. For the split, choose the closest blue, closest red. That's great. Okay, so the number of options will be linear of number of like red and blue points. Every point can be red or blue only once, so the total number of options I'm considering will be linear. So now what is left is to like, for given 2 points, I want this one to be minimum, this one to be maximum. I want to check if there is an actual split. That should be easy, right? For every point, I will pre-calculate what is the closest strictly less to the left and to the right, and closest strictly greater to the left and to the right. And so like for this point I have pre-calculated like where I can go here and here. So those ranges in the middle, they must intersect so that I can put actual split that is good both for the left and right. And then those parts will give me the rectangles, which I then calculate the union. Okay, so that sounds like a solution. So what will be going on is for every value I write down all the positions where this value occurs. Also, I pre-calculate closest to the left and right, strictly less and strictly greater for every point. That is done with like scan lines with stacks, standard sync. Now that I have those pre-calculated, now I iterate over all the ways to get number k as a sum of two numbers. Since k is relatively small, I can just iterate through all the x's, but it wouldn't be a big issue if numbers were greater, because I can just try x's that actually appear in my array. So that turned out to be not very important. Okay, so for given pair of x and y, I have position of x's, I have positions of y's. I put them in one array, then I iterate over where to put like imaginary split. Maintain the closest to the left. Well, rather, I will probably pre-calculate what is the closest blue and red, the left and right. Then for every split, take that pair and actually solve for them. When I solve for them, I look at those four values, check that those two are compared correctly. If no, then do nothing. If yes, then I need to add, like, this is a segment of left borders that is good, this is a segment of right borders that is good. They give me a rectangle together. Then I will have a lot of rectangles from all my points, and I need to find the area of their union. Okay, yeah, that should be easy enough. I said scanline with Fenwick. No, Fenwick is not enough. We need like segment tree that counts the number of minimums, because I want to know what is the total number of points that is covered at least once. Okay. In any case, I need to start by doing a lot of groundwork before I can get to the calculating the answer part. I also need to be careful when my x and y are the same value. It shouldn't be like there shouldn't be any issues. It's okay if like all my numbers are the same, so I'm just taking like pairs of consecutive occurrences. Just need to just need to not forget about it and like not duplicate the numbers. It shouldn't be a big issue. I also wanted to store vector of positions for the given value. Values are up to n. So the first thing I want to precalculate are closest smaller elements to the left and right. That is like forescan lines with stacks. Okay, great. At some point I will need a function to add a rectangle. When I add a rectangle, I will actually create two events, one at left border, one at right border. So when I do scanline from left to right, at left border I will add one on the segment corresponding to the y coordinates, and then when I reach the right border I will subtract one. So at any moment I will have, for every y, the number of times it is covered by some rectangle I have, and the number of points that are covered is the number of non-zeros, which I will count as everything minus the number of zeros, and the zeros will be counted as number of minimums, because I know that all the elements are non-negative, so I will maintain minimum and the number of minimums, which can be done in segment tree. That's just a standard problem. For here, and I need a lot of events. So for every rectangle I add two events, and also every point can be used once as x and once as y. Yeah. So maybe I need to multiply by 2 more, but I don't think so. I think that's fine. But the correct way to proceed is obviously put 8 here. But I think 4 is good enough. All right. So after I precalculated my borders, I now iterate over x, calculate the corresponding y. If it is too small or too big, it's bad. Otherwise, so I want position and want to know the value. Don't forget about the case where x and y is the same. I don't technically need sort here because like both of those arrays were already sorted because I fill them left to right here. So instead of calling sort here, I could have called just merge because I have two sorted arrays and I want like their sorted union, so that's just merge. But it doesn't mess with my complexity, so I don't bother. But technically, it wouldn't be hard, and like it is faster. But if it doesn't mess with complexity and you're not trying to squeeze every millisecond from your runtime, which I'm definitely not doing, I think it should be more than fast enough. Just simpler is better. Okay, so now for every border I want closest x and y, and I think I'm just recalculating them. I don't need 2n here because like even though I'm taking the union of two arrays, which technically can be of linear size, I can only mention every position once, so it is bounded by n. So prefix is not inclusive, suffix is inclusive, so it's like this. I can start iteration from 1 here. But like from 0 to size inclusive should also be fine. So if I have some x on the prefix and some y on the suffix, I can try to call like solve ref I solve I. Technically, I'm probably calling solve with the same parameters several times. I don't have to do it, so I can like remember which pairs I already tried, and if I'm calling with the same two parameters, just don't do it again. But again, it is not detrimental to the complexity, so it's fine. Okay, so I called solve, and now I have everything I need. So like all the rectangles are added. Now I just need to sort them. And go through the list. So here I will need to use a segment tree which I didn't copy yet. But it will be like add-on segment pos 1, 2, 3, pos. And then just get on the whole array and subtract the ones, the zeros I don't need. So technically just the root. It's good. And to answer the length of the array, so all the elements minus the zeros. So if I val is 0, then int, otherwise don't subtract anything. That's it. Okay, so now I need to write solve of two positions. So solve want to check that it is possible to take minimum on position V and maximum on position U. And if yes, then add the corresponding rectangle using this function. So I'm checking V, so smaller on the right, bigger on the left. So if that's then bad, otherwise I can put a split between them, and the corresponding rectangle I need to add would be 0, 0, plus 1, V plus 1, U plus 1, B 1, 1. So this is the position of elements strictly less, so I want my border to be strictly to the right, so it starts from here. It should be strictly to the left of V, but that like, so last good position for left border is V, and I want it to be half interval, so +1, strictly to the right of U, the right border, so it's at least U +1, and strictly to the left of this, which is strictly less, but I want it to be half interval, so without plus. Well, that was a short solve function, and now I need to copy paste the segment tree. So my segment tree, okay, so updates are just add on segments on plus. The val has value and the number of them. The value of minimum. So it's like this. And the number of 0. Okay. Okay, so let's make it more correct here. So I will actually create n zeros, and so ask get on segment, and then subtract from n, because the zero of that minimum operation is the value when like the node when value is infinite. So the values that I have not created will be like that and not zeros. So this is more correct. And I need to actually create that segment tree. That makes sense. Okay. Well, I'm assuming that I just didn't add any rectangles, so let's see which rectangles I added. Yeah, I just didn't add any rectangles. Did I call any solves? I did. So in this array, I tried to call solve 1 4, which is like this is a minimum and this is a maximum. This is good. So I should have added some corresponding rectangle. Okay, let's see what values I calculated with my stacks. So for 0, there is nothing to the left, so it's -1, -1. There's no value smaller on the right, so it's 5 and 1 here. That sounds right. So yeah, those stacks looks good. Oh, I guess I switched like 0, 1 and 1, 0 here, right? So the first parameter is the side. So yeah, this should be on the right but smaller, and this should be on the left but bigger. Still bad. Okay. Now I did add some rectangles, but both of those are empty. Solve 1, 4. I guess it still should be possible here. And also, okay, so let's run it, but it will crash somewhere, right? Or something. I need bigger segment tree because I have n+1 possible borders. No, still bad. 1, 2, 5, 6, 2, 3, 4, 5. Well, that seems right. Okay, this looks good. Okay, I can just submit it. I would not be surprised if I overkilled it, but like the flow of the solution was like very natural to me. Half a second, very fast. Yeah, so start by fixing the split because it seems easier, then actually fix where the minimum and maximum are, then yeah, I'm always remembering like the possibility that I will overcount something, and here I'm actually like not only I'm overcounting on the basis of fixing the split, which I don't actually do, but I'm might be overcounting on the fact that like I'm fixing the position of minimum and maximum. So there might be different ways to do that for the same good array. So yeah, since that is always that is the first thing I'm thinking about, I have thought about like this that I will need to end the solution by like creating those rectangles and then calculating the union. I know that it can be done, and like that simplifies the problem a lot for me. Maybe it's not actually necessary, maybe you can do without, but it is easier for me to like forget about the fact that I might be overcounting something. Just don't count, instead generate rectangles. We will deal with overcounting later. Like we will generate all the rectangles we need to count, and then instead of just adding their areas, we will like use this like absolutely independent thing, like that scanline with segment 3 has nothing to do with the problem. I just solving the problem was about generating the rectangles, and then to get the final answer, I need to take area of their union. I know that it can be done. I know that I can do it. So from that point, I'm focusing on how to generate the rectangles, and that is much easier for me because I don't care about overcounting anymore. I'm just focusing I can fix anything I want, and just for when I fix it, what are the good rectangles with all that considered fixed. And if I generate all of those rectangles, I will then count the correct answer later. And when I fix the positions of minimum and maximum, turns out that it's very easy. That was the solve function solves for positions of v and u. Okay, I needed to pre-calculate those arrays, but that's also 4 scan lines that are exactly the same. Yeah, the last part I needed to make it work is to make sure that the number of pairs I'm considering is linear, and to do that, use this fact that k is fixed, and I can consider fixed x and y, and then for fixed x and y, generate linear number of options I need to check. Very flowy solution for me. Every step just follows each time I'm making the problem simpler by saying, okay, I can I have an issue, I can solve this issue by doing that, and now I need to solve the same problem but without that issue I was worried about. And that's what problem solving is for me. So very satisfied with how that turned out, even though the solution in the end is a lot of data structures, right? Some scan lines with stacks, some stuff here, then in the end scan line with segment 3. It would, by the solution, it looks like I would not enjoy solving this problem, but the actual solving the problem was just okay, I can use this data structure I know to resolve this issue I think that I have, and now I have one less issue to worry about. And all those parts are very independent, very nice. Well, I wouldn't say it was my favorite contest, but all the problems are alright. I don't know, nothing really stands out. Problem E was probably the most interesting in terms of actual solving. The problem about source was fine. And F, I mean, I don't really like it, but I really like how the solution, how my solution was flowing, one step at a time. Very, very satisfying. Thanks for watching. Bye.